So last time we reviewed continuity and momentum and energy equation. The last thing we want to review also is the thermo, especially the second law of thermodynamics. Alright? So sometimes the second law of thermodynamics seem like it's not really relevant. Like there's too much, like the first law is all we need in life, you know, which is Q minus W is du for a system, or Q minus W equal to m dot H plus half V squared plus GZ at the outlet minus m dot H plus half V squared plus GZ for the inlet. But the second law sometimes really makes sense and is very important. And in this course, when we start dealing with shock waves, and that mass will take us all the way up to give us two solutions. Two possible solutions will be valid mathematically. The shock could be this or this. It's the second law that basically tells us that the first solution is only mathematical, doesn't exist in real life. Only the second solution will exist. And here, this is the one that you should take. Right? How would that work for us? Like, whenever does the second law really tell us to reject something? It's like, you know, this, if you put a piece of ice, very cold, huh? Next to a piece of hot iron over here, very hot. You put them next to each other. The first law of thermodynamics will basically tell you if there is heat transfer between the two of them, and there's no heat transfer to anything else, you know, you just put them next to each other. The first law will tell you 100 joule will move from one to the other. But the first law will not tell you that the ice will actually melt and the hot iron will get colder, because the 100 joule will go from the hot to the cold. The first law will basically tell you 100 joule will move between the two of them. But you know, he doesn't mind that the ice will give 100 joule to the hot iron. So the ice get even colder and the hot iron get even hotter. Of course, you know from physics it doesn't work this way, right? We cannot just expect the heat transfer between this cold class and the 100-degree outside air to actually go in the way that we like, which is we want the air conditioning, the class to get even colder and the street to get even hotter. Actually, this happened only by tricking by taking the second law by using the condenser and the evaporator and the compressor in a big HVAC machine. How we do this? Because again, the second law tells us always that the temperature will move from the high to the low. So we have to bring something here that's colder than this classroom, which is the freon. You bring the freon, which is even colder. The 100 joule will move to the freon, and then you take the freon to the outside, but you know that in order to get the 100 joule out, the freon needs to be actually hotter than the air outside. So the compressor, and that's where you spend your money, take the freon from this low temperature, all the way to say 120, so that when he go outside, now he's hotter than 100 degree, and the 100 joule on top of them, also all the work that you did in the compressor, all of them get out. All right? So the second law tells us basically that which direction does the physics work, that which direction does Mother Nature operate the business. All right? And that's what we need. Right? So that's why it would be really nice if we can track the second law without having to pay in the compressor. Well, this guy is actually, including this slide, he was on the cover of there's this magazine about inventors and invention, and so he was credited by inventing basically those winglets, you know, that you see on the airplanes. They help a lot, right? And he was like, in a time where the computer was not really there that much, and he has this gift of looking at the data coming from the wind tunnel testing, and he can see the flow in his eye. He has like the data processing and the image process, everything in his head, so that he can imagine what needs to be done in order to basically improve the left and the drag. So after he finished all this business, he spent, and that's a little bit about what he did. He spent actually 10 years trying to find loops in the second law of thermodynamics. And so in the article they were asking him, are you regretting that time that you spent? And he said, no, I will do it again. So that's how important the second law is. Mathematically, the second law, sometimes it's written really in a really weird way, like this. So this is another, those three formulas are way to write the second law. Right? To put words on it, basically the second law is telling us that the entropy the entropy S increase for two reasons. Let's not say increase, the entropy change for two reasons. Alright? When you go from 1 to 2, process 1 to process 2 through the compressor or the condenser or the gas turbine, the entropy will change for two reasons. What are those two reasons? What will make the entropy change its value? First, first heat transfer, delta Q. If you have heat transfer, you can change the entropy. Okay? So a adiabatic process will look basically have zero entropy change. If I plot on a TS diagram, adiabatic process, what does adiabatic mean? No heat transfer, really well insulated. The part that will change the entropy due to heat transfer will be zero because of this. Right? If we add heating, if we add energy, heating increase the entropy. Cooling decrease the entropy. So in a TS diagram, you go to the right by heating, you go to the left by cooling. Right? This is important to remember. So heating will increase your entropy, cooling will decrease your entropy. Right? On a TS diagram. Remember in thermal? All those cycles that you plotted on a TS diagram, Rankine cycle and Brayton cycle, and so heating will take you this way, cooling will take you this way. So that's why this is the heating in the boiler and this is cooling in the condenser. Right? That's the first thing that will change the entropy. The second thing that will change the entropy, and that's what's important to us in this course, is that's energy, heat transfer. We said that. What's the second thing that will change your entropy?
Pressure.
Friction, and not just friction, all the irreversible processes, all the losses, mixing, all the things that introduce irreversibility in the system. All right? By the way, heat transfer by itself is also, it's actually irreversible. If 100 joule came from the wall into our class from the hot air outside, we cannot tell them get out. It cannot be reversed. We have to do a lot of tricks in order to bring them out again. So heat transfer across temperature difference, which always the case, the heat transfer always come from high to low. That's not reversible. So a heat transfer will have two parts. Part that's just the heat transfer that will increase the entropy by itself, but also the other part is the irreversibility associated with that heat transfer. All right? Very good. So then what this means that for adiabatic process, the heat transfer part will not change the entropy. And isentropic process, that's not just adiabatic, that's also adiabatic and reversible. Isentropic is like super adiabatic. It's like adiabatic and reversible too. Alright? So not only you don't allow heat transfer, but you kill all the friction and every way that losses can creep into your system. So how much entropy you would expect for isentropic process then? How much entropy change? Zero. You killed the heat transfer and you killed all the friction and irreversibility. So isentropic process on a TS diagram will go up like this on a TS diagram. So isentropic compression, isentropic expansion in a compressor or a turbine, there will be vertical lines. Right? No going to the right, no going to the left. But if there is irreversibility in the system, because no compressor ever built that has no losses, no friction. That's in our dream, right? So ideally, the compression in the compressor in the gas turbine engine, in the jet engine, ideally he will go up, but in real life he should go to the right or to the left. To the right, because it needs to increase the entropy. It needs to add some irreversibility. There is some irreversibility that will change the entropy plus. Right? So back again to the statement of the second law. So basically you can say it's delta S irreversibility greater than or equal 0. Meaning that at best the delta S irreversibility will be 0. That's for reversible process. Or it will be higher than 0. all right? Or the other way to see that second law is basically this, that delta S is greater than or equal delta Q over T. Why? Greater by how much? Greater by the irreversible part. So that's kind of the total entropy change in a process. It will be this, and on top of it, a little bit irreversibility. And that irreversibility is always, that delta S due to irreversibility is always plus. All right? So to tell you the truth, when I was undergrad, this didn't really make sense to me. It's like was really very hard to appreciate until you put it into a cycle. Then you really realize how important this thing is. So let's look at a gas turbine cycle. What do you call this cycle? This is 2 pressure, constant pressure, and 2 isentropic. This is the Brighton cycle. This is the ideal cycle for a jet engine. So the compressor 1 to 2, you go 1 to 2s. This is isentropic case. And then into the combustion chamber, that's where you put all the fuel and you combust. You go from 2 to 3. This is constant pressure, heat addition. So you are burning at constant pressure. Okay? You are burning at constant pressure. This is not like our car engine where we burn at almost constant volume. Right? When we basically just squeeze all the fuel and then the spark plug come and all the fire get ignited at very small volume, almost constant volume, because the piston actually start to move a little bit. Right? But this is burning in a pipe, the engine, the combustor pipe. So you are burning at constant pressure, and then you expand in the turbine from 3 to 4s, and then you either send the air out and you bring fresh air, or if the Brighton cycle is a closed cycle, so that basically you go back again here. Okay? So 1, 2s, 3, 4s, this is the ideal cycle. But now, because we just learned the second law, tell us that delta S for a process like this, that adiabatic compression and adiabatic turbine, no heat transfer in them. They ideally should go up. Ideally should have delta S equal 0. But in real life, no, they have delta S, and it's not 0. It is plus or minus plus. So the second law basically tell you, forget about this 2. The actual 2 is here. This is horrible news, that the 2 is here rather than here. Why? You see this, the difference in the temperature on the y-axis, that delta T, you multiply by CB and it become delta H. That's the difference in enthalpy. And yes, the compressor have also kinetic energy and potential energy, but they are nothing compared to the change in enthalpy at the inlet and the outlet. So when you apply the first law to this guy, the Q minus the W, and Q 0 because it's adiabatic, the power of the compressor is all about his delta H. And his delta H is all about his delta T. So the second law basically telling you that you are going higher, that basically telling you that the compressor would require more power than you think. And here in the turbine, ideally it should go down. Ideally delta S should be 0. It should be a vertical line because it's adiabatic. But the second law tell you no, you will have delta S. And delta S will send 4S to the right or to the left? To the right, so that the entropy will be plus. That's also horrible news because now the delta T on the turbine is smaller. So the turbine give you less power, the compressor require more power, and the cycle may not really run. And that was the case when they invented this jet engine on paper. It was perfect, except that it didn't really work because the turbine was always consuming, and not that the turbine, not only the turbine is supposed to run the compressor, it needs to also have more work, right? Because that's why we are burning the fuel, not just to have a toy where the turbine runs the compressor and keep running in circle. We are supposed to get extra work on this shaft. There should be a network that run either a fan, like all our now most passenger airplanes and even fighter airplanes, they actually run turbofan, a big fan at the beginning. It's different from the propeller. The propeller is like for heavy cargo, We have the propeller and very cheap passenger airplanes. But then the fan is really most of them are using fan now. Or in the old time, just the turboprop. That was the case. Or if this was for power generation, like I guess the gas turbine that we have here in Jenks power station, they have 2 gas turbines. The shaft is actually connected to a generator that generates electricity for us. But anyway, the point is that you're supposed to get extra work, right? And so the entropy, or the second law really, is eating from your share in both sides, right? So that's how important it is. And he will help us in chapter 4 when we get, I'm telling you, 2 solutions. One of them will increase the entropy, one of them will decrease the entropy, and we will just have to say, no, the reversibility will always have to increase the entropy. So that mathematical solution that will decrease the entropy, this is just for paper, it doesn't really work in real life. Right? That's how important it is. So out of the first law and the second law, if you follow this, this is also in your textbook. If you follow, this is just simply the first law of thermodynamics for a system, a piston or cylinder where there is no inlet and outlet. Things just basically contained in a volume. Delta Q minus delta W equal delta U. The Q minus W equal delta H, M dot delta H, that's for an open control volume, a pipe, an engine, stuff coming in, stuff leaving out. But if you have a piston with a cylinder, things are contained inside the system, it's delta Q minus delta W equal du. And if you assume isentropic, reversible to start with, then delta Q will just simply become TdS. There is no extra delta S irreversibility. Alright? So you can basically say that delta Q is TdS. And so you arrive at this, and then realizing that the enthalpy is U plus PV, or dH equal, let's differentiate, so it becomes du plus PdV plus VdP. If you take this du out and put dH, and those two guys, one of them, the PdV, will cancel with this, and you will end up with TdS equal TH minus VdP. Those two equations, one of them in terms of du and one of them in terms of dH, if you integrate those guys, you will reach a relation for the entropy change. Okay, this is the reversible part. So S2 minus S1 is CB ln T2 minus over T1 minus R ln P2 over P1, and the other relation, the du, will result in, rather than CP, you will end up with CV. So why those two equations are important? So this gives us the entropy change for a process. Now if there is no entropy change, because the process is isentropic, so first of all, it's reversible. So because it's reversible, delta Q was equal to TdS, so there is no irreversible part. But on top of that, even delta Q is 0. So that makes delta S equal 0. So for isentropic process, if we put this guy equal 0, that will give us a relation between T and P. And that's what this slide is all about. This slide is basically telling you that for isentropic flow, isentropic process, the T and the P, they are related to each other. How? Put this equal to 0, here delta S equal to 0, you'll end up with CB ln T2 over T1, this guy equal to this guy. Or in short, this thing in red here. How did this show up? Well, because the CB, see that CB is gamma R over gamma minus 1. The thing in green, that's CP. So if you take CB and write gamma R over gamma minus 1, R can cancel with R, and then you have this power multiplied by ln, and of course if you have x ln something, ln y, then it's ln y to power x. You take this and you put it on top of the power. So for isentropic process, P2 over P1 is T2 over T1 gamma minus 1. So this line, a lot of students actually forget, and so it would be important throughout the course. And then they will say, well, how do we come up with the pressure? One of the really big homework problem would require you to know that if you know the temperature, at the end you should be able to calculate the pressure. That's how. If it's isentropic, that's how. Right? And the same thing from the other equation, you can relate the T and the rho. the second equation, which is this. Again, for isentropic, this side will go to 0, then this will become equal to this. The CV can be written as R over gamma minus 1. Cancel the R with the R, take the power on top of this guy, and you have a relation between the V and the T. Actually, the difference, the V is the inverse of the rho. This is not the velocity. What is that V throughout this thing? What was that V? That's the specific volume. Excellent. So it's 1 over rho. So that's why V1 over V2 is root 2 over rho 1. So in short, here is a relation for isentropic. Again, for isentropic flow, isentropic process, this is how it will work. And I want you to mark the page on chapter 1 where this thing is with a star or something, because out of chapter 1, that's the most important page that you want to go and refer to it. So which page is that? 26? Right. So on page 26, make a star on the corner. Right? Because that's where this equation is. They tell you, if you know the temperature ratio, how you can get the pressure ratio. Or if you know the pressure ratio, how you get the density ratio. All right? Questions? Very good. And I'll finish chapter 1 by talking about this simplification, that throughout the course you'll find that, you know, we'll have all those area change, and you'll find that I'm always basically saying that the flow is one-dimensional. Okay? So in real life, the flow is not really one-dimensional. There is a little bit of 2D. Because, meaning there is also vertical velocity. They are not just all moving horizontally. How can I prove that there is vertical component? Well, didn't they move from this low to this high? Huh? I mean, there must be some vertical displacement, but its magnitude is very small compared to the horizontal. So the 1D, so this is pretty important. A lot of really complicated problem, you know, can be simplified to 1D. And you can get not the exact results, but very good results. But you get them very quickly, right? So people can simulate flow in a very complex geometry by saying, well, let's just do it 1D first, right? And of course, if they want to really go after all the details on the corners, and well, you cannot handle the corner with 1D. You have to go for 2D simulation, right? But we will do 1D. And so this finish chapter 1.